All right, so you probably heard the hype around Mamba, right? The so-called transformer killer with its insane efficiency. But it's got this secret weakness, a memory problem. It can actually forget really important stuff. So today, we're going to dig into 3 brand new papers that are basically in a race to fix this core, fundamental flaw.
So here's the game plan. First, we're going to talk about Mamba's big promise, but also its big paradox. Then, we'll really explain that memory bottleneck. After that, we'll dive into the 3 solutions: more internal memory, a kind of middle ground, and then looking outside the model entirely. And we'll wrap up with the big, no free lunch takeaway.
Okay, Section 1, Mamba's promise and paradox. Let's get right into it. Mamba and, state space models in general, SSMs, they really showed up on the scene with this absolutely huge promise. So the big deal was this. They totally broke free from that quadratic scaling that, let's be honest, plagues transformers. What that means is, if you double the length of your input sequence, the compute cost doesn't go up by 4 times, it just doubles. It's linear. And if you've ever worked with super long sequences, you know this was an absolute game changer.
But of course, there's always a catch, right? Researchers pretty quickly started noticing this consistent failure mode. It kept happening on tasks where the model had to remember something specific from way back in a long context. So think about it. You ask a model to summarize a huge document like 100 pages, and it completely forgets a key name that was mentioned right on page 2. What's going on there? What's the trade-off?
All right, that brings us to the memory bottleneck itself. To really get what's happening, we need to kind of visualize how these 2 different architectures actually remember things. Okay, so first, let's talk about standard attention. The best way to think about it is like a perfect recall filing cabinet. I mean, it stores everything. Every single key and value pair from the input gets its own file, so you can go back and pull any specific piece of information from anywhere in the context. But, and this is the big but, the cost of searching through and maintaining that massive, constantly growing cabinet is what gives you that O of n squared complexity. It gets expensive fast.
Now, on the other hand, you've got an SSM, like Mamba. This is way more like having a single notepad with a fixed number of pages. It has to compress the entire history of everything it's seen into this one fixed size state. It's super efficient, yeah? But that compression is what we call lossy. New information can literally just overwrite or smudge older notes. It's fast, but not everything gets saved.
And this quote really nails it. The fixed size state is a lossy compression of history. That lossy compression is both the source of efficiency and the source of limitation. So the crucial point, the thing to really remember, is that the very thing that makes Mamba so fast is also its biggest weakness. Okay, so how do we fix this bottleneck? Let's look at solution number 1, which is all about adding more internal memory. This one's called mixture of memories, or MUM, and it takes probably the most direct approach you can imagine. The whole idea behind mixture of memories is pretty intuitive. It basically says, hey, instead of one single notepad that keeps getting overridden, what if we had a bunch of smaller, specialized notepads? And then you have this clever little router network that looks at the incoming information and decides which notepad it belongs in. So, facts about people go in one, dates go in another, and they stop interfering with each other.
So where's the trade-off here? Well, you're paying the cost inside the model itself. The model gets bigger, right? More parameters. And it gets more complex because you have this new routing logic. But the big benefit is that the whole system is self-contained. You don't need any extra databases or anything in inference time. It just works.
All right, solution number 2 takes a different tack. Instead of just picking one extreme, it tries to find a middle ground. This one's called log linear attention. So log linear attention, as you can see, tries to find this sweet spot right between full attention and a pure SSM. So instead of just one single fixed-size state, it actually maintains a set of states that grows as the sequence gets longer. But, and this is key, it grows much more slowly than with standard attention. It grows logarithmically. And how it does this is actually pretty clever. It uses a structure that keeps the really recent stuff, the last few tokens, in super high-resolution, fine-grained detail. You can think of them as tiny little memory buckets. But as information gets older, it gets summarized and compressed into bigger and bigger buckets. So it's not forgotten, just summarized. This means you're paying the cost and the complexity of the attention mechanism itself. It's a true middle ground between those 2 extremes.
Okay, on to our 3rd and final solution. This one basically says, you know what? For some problems, this limitation is so fundamental you can't just solve it by stuffing more memory inside the model. The answer, they argue, is to look outside. Yeah, this paper makes a really bold claim. I mean, listen to this quote. We show a simple theoretical result stating that SSMs cannot accurately solve any long-form generation problem, undermining their main competitive advantage. Whoa! So what they're saying is, because of that fixed memory, SSMs are just fundamentally broken for certain long tasks, and no amount of clever internal tweaking is going to fix that.
So what's their solution? Don't even try to fix the internal memory. Just sidestep the problem completely. Give the SSM access to external tools. Let it talk to a database or a file system or some other retrieval system. That way it can just offload its memory. It can write down important stuff and then read it back later when it needs it. This gives it a practically infinite memory space.
All right, so we've seen 3 very different solutions to the exact same problem. So what's the big picture here? What's the real takeaway?
And this table, I think, really sums it all up beautifully. The big takeaway is that there's just no free lunch. All 3 of these are basically just variants of add more state, right? But they each choose to pay the cost in a different place. MOM pays the cost inside the model, with more parameters and complexity. Log linear pays it in the mechanism, with more compute. And the tool use approach pays the cost outside the model, by creating dependencies on external systems.
And look, these 3 papers are really just part of a much, much bigger conversation happening right now. You've got other work like Mamba 3, which is improving the core state space design itself. You've got pruning methods that are trying to make these models smaller and more efficient. It's a really active area of research. So this all leaves us with a really fascinating question for the future of AI architecture, doesn't it? As we keep pushing for longer and longer contexts, which of these trade-offs is going to win? Are we just going to build models with bigger and bigger internal memories? Are we going to find ever cleverer middle grounds? Or will the future belong to models that are just really good at talking to external tools? Hey, if you want to go deeper on topics just like this, you should definitely subscribe to the LLMs research newsletter. And of course, follow the show on Spotify, YouTube, or Apple Podcasts. Thanks for watching.